Good afternoon, everyone. I'm Lin Ding from the University of Minnesota. Today, I will present my research on bioelectrochemical treatment of dairy manure for in-situ sulfide remediation. Okay, so my talk will cover three aspects. First of all, I will talk about the hydrogen sulfide formation and removal methods. Second, I will introduce our lab-scale bioelectrochemical experiments and the results. Finally, we will move on to our pilot-scale demonstration using this BEC technology. So, hydrogen sulfide, Before talking about the treatment process, we will first introduce the hydrogen sulfide, or H2S. Hydrogen sulfide is a toxic, corrosive gas with an acute rotten egg odor. It's dangerous even at very low concentrations and can be fatal above 700 ppm, which is quite low actually. According to the Bureau of Labor Statistics, hydrogen sulfide is one of the leading causes of workplace gas inhalation fatalities in the United States. Therefore, hydrogen sulfide is generally considered a safety hazard to all organic waste handling or process which may contain sulfur. So in dairy manure, hydrogen sulfide originates from sulfur-containing feed, bedding materials, and also the animal waste. Sulfate-reducing microorganisms convert sulfate into sulfide under anaerobic conditions, and manure storage and handling will release significant amounts of hydrogen sulfide gas, which will affect the farm worker safety, also the cause health, and it will also be very corrosive to the facilities and reduce the equipment lifespan. Several methods have been developed to remove hydrogen sulfide from manure gas, including, first of all, increasing ventilation to disperse hydrogen sulfide in the barns. Second, gas phase removal using iron-based absorbents or biofilters. And third, the in-situ treatments such as microaeration or chemical dosing. While these methods have varying degrees of effectiveness, many require additional facilities with high operational costs and chemical inputs. That brings us to our proposed approach, the bioelectrochemical or anode oxidation method. So bioelectrochemical or BEC systems offer a promising alternative by leveraging the microbial activity and electrochemical reactions to mitigate emissions. In our system, an applied voltage from an external power supply facilitates multiple sulfide removal pathways, mainly including, first of all, inhibiting the sulfate reduction performed by the sulfate-reducing microorganisms. Second, the biotic oxidation, sulfide oxidation by microbes inside the anode biofilm. Third, the mediated oxidation assisted by the anodic oxygen generation. Third, the abiotic sulfide oxidation at the anode. And finally, the metal sulfide binding or precipitation assisted by the metal ions released from the anode oxidation. So by integrating this approach into manure management, we aim to reduce hydrogen sulfide emissions efficiently while maintaining the smooth anaerobic digestion performance. So this is our proposed treatment process. The overall objective is to develop a microbial or bioelectrochemical mitigation technology for hydrogen sulfide release from dairy manure storage. We started with lab-scale experiments to evaluate the performance of different electrode materials and configurations as well. The key aspects we tested include the impacts of different sacrificial and non-sacrificial metal anodes on hydrogen sulfide removal and the feasibility of a short-term BEC pretreatment, which separates BEC and AD stages to before the anaerobic digestion. So in this experiment, we tested several different sacrificial metal anodes, including low carbon steel, LCS, aluminum, AL, and copper, Cu, against a durable titanium cathode, Ti. All results showed that low carbon steel and copper had the highest hydrogen sulfide removal efficiency, while aluminum actually was not effective in removing the sulfide from manure. We can also observe different precipitates or attachments on the electrode surface after the experiment. Apart from hydrogen sulfide removal, we also examined biogas production on our collaborating farm. The manure in the transition pit will be pumped into the anaerobic digester for further organics decomposition and biogas generation. Therefore, we hope that the BEC treatment can improve the biogas generation or at least not negatively affect the subsequent AD process. So our findings revealed that the thin low carbon steel did not affect the methane yield, but it lowers a lot of the hydrogen, the COD, the CO2, carbon dioxide release. Aluminum was effective in facilitating the biogas production by improving the methane yield and also reduce carbon dioxide. But copper was toxic to the anaerobes producing gas, which resulted in a huge decrease in both the methane and the carbon dioxide production. Therefore, we can conclude that low carbon steel anodes could be a viable material for balancing the hydrogen sulfide removal and the biogas production or the biogas quality. So next, we tested the non-sacrificial metal anodes, aiming at reducing the anode material consumption. They include stainless steel, SS, titanium, Ti, and mixed metal oxide. Unlike the sacrificial anode, these materials did not release metal ions for sulfide precipitation at a low voltage. The results showed that none of these non-sacrificial anodes effectively removed hydrogen sulfide from manure. So we can say that anodic oxidation alone without metal sulfide binding was not strong enough to reduce the sulfide release from manure storage. To simulate the real farm conditions, we further separated our BEC treatment from anaerobic digestion of dairy manure and further tested the short-term BEC treatment or pre-treatment before anaerobic digestion. We applied an external voltage for 24 hours to the manure first, then subject it to anaerobic digestion without the BEC system. With the increasing voltage, we can see that manure became darker and darker with the formation of more black insoluble ferrous sulfide precipitates. And these are the hydrogen sulfide removal and biogas production results. We found that all bio-electrochemical groups showed hydrogen sulfide removal, but a voltage of over 1.5 watt is required to secure a high sulfide removal efficiency of over 89%. Meanwhile, the methane yields remain stable across all the treatments, while carbon dioxide emissions were slightly reduced, therefore improving the biogas quality. Another thing we want to emphasize is the technical digestion time, T80, which means the time required to produce 80% of the maximum methane yield was shortened by 3 to 5 days, which potentially accelerated the biogas production and enhanced the operational efficiency actually. So after obtaining these promising lab scale results, we moved on to a pilot scale demonstration at our collaborating farm. The goal was to assess how the BEC system performs under real-world conditions. So to do this, we designed and installed a larger BEC system. So larger pieces of low carbon steel anode and stainless steel cathode were mounted on a PVC holder. A frame case was built to enclose electrodes and separate the BEC treatment chamber and the control chamber. So the system was installed in the manure pit and operated under farm conditions for over 2 months continuously. We monitor the hydrogen sulfide levels continuously using the analyzer and track the change over time to evaluate the treatment effectiveness. Let's look at the results. Our pilot scale data showed a significant reduction in the hydrogen sulfide emissions, actually. The hydrogen sulfide level drop in the BEC treatment chamber headspace corresponds to an almost 80% reduction compared to the control chamber without the electrodes. And it also shows a 60% reduction compared to the open air inside the barn. These results confirm that our BEC treatment effectively mitigates hydrogen sulfide emissions at scale. Another important factor we observed was the influence of temperature on the hydrogen sulfide levels. During the winter, actually the overall hydrogen sulfide emissions were lower due to the reduced microbial activity in the manure. However, in warm seasons, the emissions increase a lot, which makes the RBC system more crucial. So then follows a key question: how does BEC treatment compares to other in-situ sulfide removal methods in terms of the cost? Although currently, rarely none was actually used in dairy manure storage. We conduct a techno-economic analysis comparing BEC treatment to typical chemical dosing methods in literature, including ferric chloride dosing, ferrous chloride dosing, iron oxide dosing. This analysis used our local collaborating dairy farm with 1,800 cows and consider the installation operational costs and material expenses over a 10-year operation period. This is the cost breakdown of the 4 treatment methods. So we can see that actually the ferric chloride dosing has the lowest cost per year due to its cheaper chemical price as a byproduct from the mining industry, while the cost of RBC pretreatment is lower than ferrous chloride and iron oxide dosing. Although ferrous chloride dosing has a lower upfront cost, it requires continuous chemical input and replenishment. And the oxidative stress caused by the overdosing of ferric ions may impose harm to the anaerobes in following anaerobic digestion. But in contrast, our BEC system was proved to improve the biogas quality, accelerate the biogas production. While the BEC treatment using the electrodes can also minimize the need for recurring anode replacement. Besides, it still has a lot of room to further improve or optimize the treatment to reduce the expenses. So to summarize, our lab-scale BEC treatment significantly reduced the hydrogen sulfide emissions by 89 to 100% from dairy manure. Sacrificial metal anodes, low-carbon steel, are most effective in hydrogen sulfide removal with improved anaerobic digestion performance. Our pilot-scale results confirm its feasibility with up to almost 80% hydrogen sulfide reduction, and the long-term costs are competitive, making the BEC treatment a promising alternative to chemical dosing. So we want to appreciate the funding support from the USDA NRCS CRG project. Thank you.